This meeting is being recorded.
Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Valerio Proietti, who is from the University of Oslo, Norway, not the United States. I found two Oslo in the United States, but I don't think they have the University of Oslo. So it's Valerio from Oslo, Norway, and I suppose originally you're from Italy, right? Am I right?
Correct.
Excellent. And you will also act as the terminator because you are the last speaker of this academic year. So
Okay.
after we are done with questions to you, we will announce holidays. Okay, so without any further ado, Groupoids with Torsion-Free Isotropy and their invariants. Valerio, the Zoom is yours, the floor is yours. Take it away.
Thank you. Thanks for the introduction. Also, thanks for the opportunity to give this talk. So also thanks for organizing a workshop in February where I was invited here. So the talk for today. So as you can see, Groupoids with torsion-free isotropy, and it's going to be split into two parts. And right when I need to change slides, is it working? Has the slide changed?
Yes.
Yeah, they are changing. Yeah, perfect. Yeah.
Okay, because there was a bit of a lag. So the invariance is going to be mostly on the second part, so section 3 and 4. But since this talk is rather long, I thought I would start a bit slow and give you some basic definitions. I'm sure many of you are very familiar with this, but I think it's good to at least agree on the basics. And most importantly, in section 2, I want to give you many examples because, of course, it's okay to be interested in abstract groupoids, but I am also more interested in dynamical systems that give rise to groupoids. So I want to give you like a little collection of different dynamical systems of different flavors that give rise to groupoids. So this is the plan for 1 and 2, and 3 and 4. I'm going to pick up the pace, go a little bit fast, and maybe give less definitions and more like sketch what I want to do. And hopefully by the end, we have a good idea of how to put together these things. The last thing I want to say is that all of this is joint work with Makoto Yamashita, and it's work from 2 or 3 years ago. We have some more recent things, but for this talk, I'd rather talk about these things to make it a bit less dense. All right, so let's start with what a groupoid. What is a groupoid? So it's a small category where every morphism is invariable. So this small assumption is more of a set theoretic condition. We don't need to be too worried about this. Just we want objects and morphisms to actually be sets. And so maybe a little bit more with more words. We have G2 is the set of composable arrows. So these are the morphisms that we can compose. So the range of one will match up with the source of the other. And G0 are going to be the objects, which we usually call units. And then the domain and codomain of a morphism are usually called source and range. And so we have these maps from G to G0. Now I also want to be able to restrict the groupoid. So if I take a subset of the unit space, G sub A will denote all those arrows whose source lies in A. And G upper A will be all those arrows whose range lies in A. And then, of course, I can take the intersection, which will be effectively restricting the groupoid to A, because then I will have arrows which start and end in A. So here's a very simple groupoid. I want to use this also to explain a bit about isotropy. So this picture is nice because it gives us many things to talk about. So first of all, this groupoid is the union of two groupoids. And the one on the left is a groupoid with one object, which, as you can see, is a group because I can compose all the arrows. Now, this is also, it's the cyclic group of order 2. And so when I talk about isotropy, I mean exactly this, the arrows which have source and range, which are the same thing. So this left groupoid has isotropy, and of course, it's not torsion-free. For today, I'm going to be considering groupoids which have torsion-free isotropy. So I do allow isotropy, but I don't want torsion. So on the right, you see an example of a groupoid which not only is a torsion-free isotropy, but it is actually free. So sometimes it is called principal. I like free a little more, borrowing from the language of group actions. Free simply means that, except for the units, an arrow will always move an object somewhere else, and there are no non-trivial arrows stabilizing objects. So another thing to say is that for these free groupoids, of course, an arrow is basically determined by the source and the range. And so we could, interpret that as the source and the range being equivalent. So for free groupoids, we're talking about equivalence relations. Okay, so I hope this is clear. Let me give just a couple of examples. So these are trivial, but they are important. So eventually we want to put a topology on groupoids. And so for the bottom one, well, okay, let me talk about the first part first. So the trivial groupoid or the pair groupoid over X is simply, as I said, we can view them as equivalence relations as well sometimes. So this is going to be the full equivalence relation on X. And so the range and source maps are given by the projection on the first and second coordinate. So when we visualize an arrow, it's better to think of it starting from the right and going to the left. So then the first projection is going to be the range. A little bit like a Japanese comic book. You start from the right, you go to the left. Yeah. And the composition is given here at the bottom. So see, in order for me to be able to compose them, I have to have the matching of the range of the right side and the source of the left side, so that Y and Y.
Wait. I have a question about Japanese comic books. Don't you also go from top to bottom, not from right to left?
Top to bottom, but you read from right to left.
I remember right to left, but the top to bottom as well, right?
Yes, that's correct.
Okay, that's important, yes.
Well, that's important. Yes, so if I have Y there in the middle, I can compose them, and the result will be X comma Z.
Now I believe that this is your joint work with Makoto.
Yes, exactly. That's my tribute. So as I said, this is one extreme. At the other extreme, I can consider just the equivalence relation of, well, a point is equivalent only to itself. So that would be the diagonal inside this. And well, that's what I want to say. If you think of it later as putting a topology on these groupoids, this last example will essentially be just a topological space. So this is important because then we already see that when I talk about groupoids, I'm also topological groupoids, I'm also including topological spaces. And so this is something to keep in mind, especially later when I talk about homology. Okay, so talking about topologies. So we usually restrict to locally compact groupoids. So I have the second countable. So for now, this is not important, but I think all of my examples will be. And more importantly, later it's actually important to have second countability for separability issues. So we want all the composition, inversion, source and range, all the structure maps to be continuous. The space of units, we want it to be Hausdorff, but there is no Hausdorff condition on the arrows. Later on, I will, well, as I say, I will somehow assume that I have Hausdorff groupoids, but you should also know that when you have a free groupoid, then Hausdorffness is automatic. So a point of G has a compact Hausdorff neighborhood, so that's the locally compact part, and the range and source maps are open. So this requirement, this is necessary, and it's related to wanting to be able to do analysis. So in order to have Haar systems, which are analogous of Haar measures, we need the range and source maps to be open. So the same way as we sometimes find it easier to work with discrete groups instead of locally compact groups, for groupoids, we look for analogs. And these are the état groupoids, and even better, the ample groupoids. So a locally compact groupoid is état if the range is a local homeomorphism, and that will also say that the source is a local homeomorphism because, again, composed with the inversion. Now, if I have a état groupoid, I can consider these nice opens called bisections. These are opens U on which the restriction of range and source are homeomorphisms onto open sets. So each point of G admits a local base consisting of bisections. And for an ample groupoid, I assume the unit space to be totally disconnected. So I will have compact open bisections that will give me a local base around the point. So maybe just one thing, you see that ample groupoids in a way, they resemble a little even more discrete groupoids because, sorry, discrete group, because a discrete group has only one unit, which is of course a zero-dimensional space. While étale groupoids, they have unit spaces which can be more general. So here's one point about non-Hausdorff groupoids. So as I said, later on I will want to assume Hausdorffness for the arrow spaces too, but because most of my groupoids will be actually free, that's actually automatic. So that this condition is not really a condition. So to explain this, let me just say a few words on this. But so it is important to understand the points in the closures of the unit space minus the unit space, they are isotropy. That's because if I take a net of units and that converges to some arrow, that arrow cannot be arbitrary because the source and the range map are continuous and I have uniqueness of limits on the unit space. So then a net of units can only converge to an isotropy arrow. So that tells me that if I am free, then immediately I see that the unit space is closed. And if the unit space is closed, then I can prove the groupoid is Hausdorff. That's because if I have some net of arrows, which is, say, converging to two limit points, two arrows, gamma and gamma prime, then I can compose this net with its inverse. And then I will get a net of units. And this net of units converges to a unit because the unit space is closed. But because composition and inverses are continuous, then I can also see that it converges to gamma times gamma prime inverse, which is where these two limit points. But if this is a unit, I'm essentially saying that gamma equals gamma prime. So limits are unique even within arrows. So by this way of proving it, I'm not sure if this is the faster way, but you can see that if I have a free étale groupoid, then it will be Hausdorff. So it's important so that to say that, later when I consider these groupoids, this Hausdorffness condition is not really a requirement. I still want to try to convince you that non-Hausdorff groupoids, of course, are very interesting, and they actually arise quite naturally when you do geometry. So you don't have to, look for some artificial example. One, famous such groupoid, and many groupoids arise as holonomy groupoids of foliations, and I just want to give you an example of this. If you don't know what holonomy is, that's fine, but I'm sure many of you know. So the refoliation is a codimension 1 foliation of the 3-sphere, and so this foliation will give us a non-Hausdorff groupoid, which is, I think, a nice example. So let me just explain how this works. So first of all, it is enough to foliate a solid torus. That's because if I take two solid tori and I glue them along their boundary, which is just a torus as a surface, then I get a 3-sphere. This is the best way to see this is just to think of the 3-sphere, the 1-point compactification of R3. So if I take a solid torus immersed in R3 and I consider its complement, then when I pinch the complement, I am effectively creating another torus.
It is also the standard keyhole splitting of a 3-sphere into two solid tori which are glued among their boundary. This is like the essence of local triviality of a Hopf vibration. So
that is correct.
Yeah.
So the formulas, I don't mind too much about the formulas, but as I said, it is enough to foliate this. It is enough to foliate the solid torus. And so I like to think of this as a collection of infinite snakes, each eating its own tail. So this is the picture. So we have an infinite collection of snakes, but also, the snake itself is infinite, and in fact, it is a plane. So you can think of the origin as sitting on the head of the snake, and then the rest of it will be a plane.
If I might jump in for a second, you see, because I think it's very interesting. I remember Richard Ness taught me this. This is an example here of a free action of R on a plane, because you don't have to have a torus. You can just have an action of R on R squared, okay? And these are just lines of some very simple vector fields, but these are exactly the snakes which you are writing here. And this would be an example of a free action with a continuous translation map. However, the appropriate fiber product is not closed in the full Cartesian product. And that's why this action is not proper. And this is why you have all this beautiful non-Hausdorffness as the effect of this foliation. Because when you go into the standard Kronecker foliation of a two torus, everybody knows it who doesn't go into geometry, then basically, for starters, translation map is not continuous, forget it. It's not a principal action, it's not proper. But here it's kind of funny, the translation map is continuous. It's just that the image of a fiber product, the fiber product is not closed in the full Cartesian product. The fiber product, I mean all pairs which are in the same orbit. Sorry, it was not necessary for your talk, but I think that there is some exciting geometry behind it. Okay.
Good. No, thank you. Yeah. So, so in order to see this non-Hausdorffness, as I said, so we got this collection of leaves, each homomorphic to R2, but then there is a middle leaf, exactly where the gluing occurs. And that middle leaf is closed, and it's exactly the torus as a surface. So by using this fact, we can easily come up with the non-uniqueness of limits.
Yes,
so as I said, we don't need to worry about holonomy, because in this case, the homotopy groupoid is also the same. And so, but what I mean here is just, so the units are just the points in the space, and the arrows are just homotopy clusters of paths, which are constrained to be lie entirely in one leaf. So that's the homotopy groupoid. And so now I can essentially define a sequence of contractible loops. They are contractible because all the leaves are just R2, but then they are converging into a non-contractible loop, which is in the torus, the middle leaf. So this gives us non-uniqueness of limits because, of course, these loops are all contractibles, so I can reduce them to a point, and then they will just converge to some point in the torus. But then if I see them as loops, not reduced, then they will converge to some loop in the torus, which is not contractible. So you will see that this sequence has two limits. Anyway, so this was just a brief excursion to understand that these are also interesting gadgets. Now, I want to try to convince you a little bit why, for at least for this talk, this torsion-free isotropy assumption is important. And so this is a bit of foreshadowing, I guess. So for the part of the invariant which is related to K-theory, of course, a good way to compute K-theory of groups and groupoids, by which I mean the K-theory of their associated sister algebras, is to use the Baum-Kohn conjecture, because that reduces the problem to algebraic topology, where we have more machinery. And so you might know for the Baum-Kohn conjecture, the notion of properness is quite important. And in fact, in the most standard formulation, the left-hand side has this universal example for proper actions. So it is important that we look at what kind of structure do we have for a proper groupoid, where then we assume that it also does torsion-free isotropy. That will give us some sort of simplified form of the Baum-Kohn conjecture. So I guess intuitively speaking, for example, for a locally compact group or a discrete group, the Baum-Kohn conjecture is really a statement about the group, but also about the compact subgroups or the finite subgroups. And so if we have a torsion-free group, then it becomes just a statement about the group and its relationship with the unit. So in the same way here, if I assume torsion-free isotropy, then the Baum-Kohn conjecture for the groupoid will be a statement about the relation of the groupoid and its unit space, which is the analogous of the unit for a group. So let me try a bit more precise. So if G is et al. And acts properly on some space Z, so denote the structure map as rho. And then, so we want to have this sort of local compact induced structure, which is what this theorem is telling us. So for each point in Z, I can find two open neighborhoods, U rho in Z and U in the unit space, and which satisfies this. So the isotropy group at Z acts on U, and if I restrict my groupoid at U, it contains an open subgroupoid, which looks like just this finite group acting on U. Remember, this GZZ, it is finite because of properness. And then the G, when I restrict the G action to Euro, it is induced precisely by this open copy, which looks like a group action, a finite group action. So by the way, sometimes I write actions from the left and sometimes I write them from the right. This is just, for example, here to emphasize that I got Euro on both sides, but I mean, there is no difference. I'm sorry if that's confusing. What this theorem is telling us is that locally, a groupoid which acts properly, locally we can understand its action and from a finite group lying in some isotropy. Now, of course, if I assume that I have torsion-free isotropy, then this GZZ will be trivial. And that's really the important part for us later on. So that's why, so this theorem, this Lies theorem is explaining in some sense why I want to have torsion-free isotropy, because I want to get rid of this GZZ. So a corollary of this Slice theorem is exactly that I can cover a proper G space, I can cover Z with opens which are locally compactly induced. And now by compactly induced, I mean that they're induced from a finite group action on a little open in the groupoid. So that's for a proper G space. So if I ask for torsion-free isotropy, then they will be locally induced just from the action of the unit space, and I don't need to worry about this finite action or this compact action. This notion of compact action, it arises very naturally when you look at Slice theorems of this type. It is used, so it is used already in a paper by Tu on the bound-count conjecture. In that case, it is considering maybe the closed version of it, where we consider closed sets. And this open version is considered in a paper of mine with Christian Bönicke, where we look at the bound-count conjecture for a groupoid. So, okay, this is just a little couple slides to understand this locally compactly induced structure that I want to simplify by asking torsion-free isotropy. So this is just to explain why the condition is useful. Okay, so as I said, I want to give a lot of examples of dynamical systems that I'm interested in, which will be sources of groupoids. And so let me go back to a definition by Smale. So he was interested in differentiable dynamics, and he looked at these systems called axiom-based systems, and these are very interesting hyperbolic dynamical systems. And let me tell you a few words about what they are. So we have a compact manifold with a diffeomorphism, and then we consider the differential. So if a subset lambda of the manifold is F invariant, then I can ask for it to be hyperbolic. And what I mean by this is that when I restrict the tangent bundle to, I need two things to happen. So first, if I restrict the tangent bundle of M to lambda, it will split as a sum of two invariant subbundles, invariant by the action of the derivative of F. And they will be called the stable and the unstable bundle. Then if I fix some Riemannian magic on M, the restriction of this differential on the stable bundle will be a contraction, and the restriction of the differential on the unstable bundle will be an expansion. So
I have a question. May I?
Yes, please.
Could you come back to this hyperbolicity?
Yeah, it's also here. So this slide is just the symbols version.
Could you come back to this previous page? So is the choice of this Riemannian metric essential for this definition?
Well, so the Riemannian magic will not be important, but you do want a way to say that you have a contraction.
Yeah, but then if you take another Riemannian metric, is this property stable under the choice of this Riemannian metric?
Well, I understand it's some Riemannian metric, so there exists a Riemannian metric such that.
So existence is a part of the definition.
Yeah, I suppose.
Mm-hmm.
Well, so
I asked,
no. So you're
Thomas,
right.
you ask my question. I'm also supposed to ask this.
So you will see that in a couple slides, I will actually move from this definition to a definition which involves only topology. and then I don't need to ask for existence actually.
Mhm.
So in a couple slides, you'll see about this.
But all this stable or unstable depends very much on this diffeomorphism, right?
Yes.
Sure. I mean, this splitting will, it depends on. So I need to have this invariant, and I need to know how the differential of f diffeomorphism behaves with respect to it.
Okay.
Okay, but
Okay,
if I could,
going back to due to Anosov,
Mhm.
Exactly. Sure.
which doesn't use a Riemannian metric.
Mhm.
Sure. And also diffeomorphisms are examples of axiomate systems. Yes.
sorry, if I could ask one more question to ensure myself whether I understood it correctly. So as you said, the existence of such a splitting is independent on the choice of metric. Okay.
Yeah.
The existence of such bundles, but what would happen if you change the metric? Is it possible that those then, okay, again, there is some splitting, but it is different from the previous one.
So the splitting is going to be fixed.
Yeah.
So we work with, there is only one possibility for this splitting.
So could you please come back to the previous slide? So what is the order of things? What is happening here? The restriction. Okay, so now first you have a splitting. First you have a map, an F in. Then you consider an F invariant subset. Okay, then there is a splitting, and for the splitting, one is able to find some Riemannian metric. Okay.
But with axiom A systems, it was in your abstract, right? I remember some axiom A.
Yeah, I think so.
Yeah.
So this is going to be a recurring example, but so I wanted to start from this because I know that this is what this, as you also said, this goes back to many years, but eventually I sort of move out from this. So I think when I give a few examples, it's going to be a bit clearer.
Okay.
Thank you.
So then lambda is hyperbolic if this happens. So this constant, of course, we depend on this Riemannian metric, but what the important part is really just the expansion and the contraction, not really the quantitatively, it doesn't matter. So to define an axiomate system, something with the hyperbolic set must happen. So there is another actually important condition. So omega f is the set of non-wandering points. So non-wandering has this flavor of, that comes back somehow. So for every neighborhood, there is some, iterated image of U such that when intersect with the original U, I have non-empty intersection. So the point itself might not come back, but something in the, something around it will come back. So this is a non-wandering point. And so now we can give the definition. So we want this set of non-wandering points to be compact and hyperbolic. And then this second condition, okay, here we can argue this is not necessarily part of the definition. The set of periodic points is dense in the hyperbolic set. So the interesting part about this is that although we start basically from this smooth category, we look at manifolds, this omega f is almost, which is really the only interesting part where the dynamics is interesting. For example, in the famous horseshoe map of Smale, we have the North Pole, and then the dynamics flows through a region in the South Pole. And this region is actually conjugate to the full 2-shift, which is a counter set. So we start with a sphere, but then the interesting dynamics actually occurs in some fractal around the South Pole of the sphere. So I guess Ruel was motivated by this, has defined a new notion of Smale spaces, which doesn't need the smoothness. So it just starts with topological spaces, and then you can find neighborhoods on which you can give coordinates. So the definition of Smale space itself is quite opaque, I would say, but the examples that I'm going to give, I hope they will clarify it. So I want to give you a series of examples to show that we have many different types of dynamical systems. So combinatorics nature, coming from geometry, coming from number theory, also coming from group theory. So this definition really encompasses a lot of interesting dynamical systems. So let me start with the easy one, please.
I have a question. Could you come back to this fractals? Fractal-like nature. What do you mean exactly by that?
But he likes fractals.
I mean that very often this omega f will be as a topological space of dimension 0, topological dimension 0. But then when we look at dimensions which is more suitable for a space of dimension 0, so the house of dimension, I can have several different dimensions. So that's a fractal for me.
Ah, okay. Because for instance, in complex dynamics, fractals are defined in a non-local manner. As some points whose behavior satisfies some asymptotic conditions.
For example, the Julia set of some rational function.
And so on. Yeah, so I wanted to be sure what aspect of the fractal you have in mind. Okay.
Yes, so actually the Julia set does arise as one of these uses omega f could be a Julia set for some specific dynamical system. So that's included, yeah.
Okay.
So let me start with an example which I think all of us are familiar with, which especially people who work with graph system algebras, I guess. So I want to look at shifts of finite type, and in particular shifts that are associated to graphs. In fact, any shift of finite type can be conjugate to one that is associated to a graph. So when we look at the space of bi-infinite paths on a finite directed graph, so I have vertices, edges, initial vertex, and terminal vertex. So you see I have this collection of edges, indices indexed by z, and this collection needs to be a path, which means that sort of the initial vertex of the next edge should be matching up with the terminal vertex of the previous edge. So that would be a path, and it's bi-infinite. So I have a past and a future, and I can shift this path, and this will be a homeomorphism exactly because I'm indexing over z, not over n. So I'm not forgetting my past. So we can put a metric on this, and so two paths would be a distance less than 2 to the minus n minus 1 if when these two paths, they coincide on this symmetric interval around 0 from minus n to n. So they will have the same edges in this indexing set from minus n to n. In particular, the distance will be half exactly when they will have the same central edge at 0. So at time 0, they actually coincide. So that means that I can splice them together. I can take the past from F and the future from E. That's because they coincide at 0. So this bracket map is effectively giving us coordinates. So in this ball of radius 1/2, I can give coordinates by basically expressing any other path as the past of one path and the future of another. So this is a way to give coordinates and have this is sort of should remind you a little bit of this splitting in stable and unstable bundle, but this is a topological way to express that we have a local product structure. And then the next thing should be the hyperbolic nature. So the hyperbolic nature of it should be explained in this way. So let me be even more concrete. So let's take the simplest graph ever. So one vertex and two loops. So of course, if I have a path at 0, it will either go over A or go over B. And so this space of bi-infinite path is actually the disjoint union of two groupings, exactly the ones that pass through A at 0, and then the other ones that pass through B at 0. And now for these ones, because I know that they coincide at 0, at least for when I restrict my attention to one of these two groupings, then I can give coordinates, exactly like I done before. So I can splice the past from one path and the future from another, and I can in this way obtain the whole square. So this is the local product structure. And now see the hyperbolicity. Let's look at two paths on the left. They lie on the same vertical line, so that means that they have the same x coordinate. So z and y here, they have the same x coordinate, so that means they have the same future. So at time 1, they will go through B, and then at time 2, they will go through E2, and so on. But their past is different. Now, when I apply the shift map, I should see a contraction. And of course, if I started with points which lie on the same horizontal line, then I would see an expansion. So, but let's look at this contraction. So why did they get closer? Well, see, before Z and Y, they only agreed at time 0 and higher time. But now they agree at time -1, then at time 0, and then higher times. That's because the A has gone to the left. At 0, they were to A, but after shift, the passage at A will happen at time -1. So in these vertical lines, I will have a contraction given by the shift. But these horizontal lines, I will have an expansion. So this is a sort of a pictorial proof that for this shift of finite type, I have hyperbolicity. So I want to give you examples where the local structure, so as I said, there is a local product structure, can be of different types. In this case, it's going to be just counter times counter, of course. But now I want to go up in dimension. So this is actually starts as an axiom system. Let me first give you the picture. You start with a solid torus, and then you embed the solid torus into itself. So you stretch it, and then you fold it and wrap it around the original torus again. And then you repeat this operation on this tube, and then you keep going. So this is called the Smale-Williams solenoid. So there's this map phi from the solid torus into itself. There's a formula here, but it doesn't matter. I guess what matters is that phi stretches in this sort of longitudinal direction, but then each disk, each section gets contracted. Now, if we look at this picture again, you should be able to see, of course, the hyperbolic nature of this. So obviously, in the longitudinal direction, it's expanding, right? Because the torus is getting longer, so to speak. But then when I take a section, a disk will go into 2 disks, and then it will go into 4 disks, and then it will go into 8 disks. And in the limit, I will get again a counter set.
Wait, so am I correct to understand that the number of windings of the torus over itself is increasing, right?
Yes.
Okay. Okay, beautiful.
So, but in order to, so in here, we will see that the unstable foliation will be a line. But then I want to explain how the stable foliation looks like a counter set. And for this, you need to look at these sections. So if I take a section of the torus, of course, I see a disk. But now if I take a section of this after one step, I would see 2 of them. And then they will become 4 and 8. And then in the limit, this will be a counter set. So exactly. So basically, I can take the image of phi onto the solid torus, and then I have a nested intersection, and I can take this infinite nested intersection, and I will get my hyperbolic set lambda. So of course, this is a nice picture, but in formulas, it's actually better to conjugate lambda with a better presentation. And it turns out that it's very simple. It's just the projective limit of the squaring map on the circle. And so from here, you should see that the unstable foliation is locally like R, and the stable foliation is locally like a counter set. I just want to give this example too. So we saw something combinatoric or symbolic coding. So these were the shifts of finite type. So we saw something a bit more geometric, like this Smale-Williams solenoid. Now something a little bit more number theoretic. So this example can be actually expanded quite a bit, but just for the sake of concreteness, we look at this. So we fix 2 primes, Q bigger than P, and then we look at p-adic numbers times line times q-adic numbers. And then we look at the map, which multiplies by Q over P. Now, of course, if I consider P inverse, this will expand on the p-adic numbers, while Q will be an isometry, because Q is co-prime with P. Now, of course, because Q is bigger than P, Q over P will be an expansion on the real line. That should be fine. And then dually, Q will contract on the q-adic numbers, multiplication by Q, I mean. And then P inverse is going to be an isometry once again. Now, I had this assumption that the hyperbolic set must be compact, and this space is not compact, but there is an invariant lattice. So this is this ring extension of Z by 1 over PQ. So I can mod by this, and I get a compact set. And F will induce a self-homomorphism of X. Now, if we look at the local structure here, so let's look at, for example, the unstable foliation. So this is where I should see the expansion. So I see an expansion on the p-adic numbers and on the real line. So here, the unstable foliation will be R times Cantor. Before it was just R. And for the shift of finite type, it was Cantor. So you see, you can have actually even combination of the two. So, and the stable foliation, where I have this contraction, is just the q-adic numbers. So I have another copy of Cantor. This is locally. This is the local product structure of the unstable and the stable coordinates. So now the dimension went up by 1. And lastly, this is, I guess, cornerstone of non-commutative geometry in a way. So this would be like the Kronecker foliation, but so there's going to be 2 of them and transversals to each other. So what you do is you take a hyperbolic matrix. So that means you diagonalize and you see an eigenvalue bigger than 1 and one smaller than 1. And then it preserves the lattice, Z2, so it descends to a map of the torus. Now, of course, if I am away from where the gluing occurs, then I can give coordinates using the eigenlines of this matrix. And of course, I will see expansion on one eigenline and contraction in the other. So the picture will look like this. And now the local structure is R times R. So you can imagine that later on, the groupoid sister algebra that associate to this would be, of course, the one of the, basically, the Kronecker foliation, and it would be more equivalent to any rational rotation algebra. Okay, so this is my sort of list of examples. I hope I convinced you that we can get a lot of interesting phenomenon. We can actually have more. For example, we can have examples coming from self-similar groups. And we mentioned before the Julia sets associated to rational functions. But I think we've seen enough. So how do we get groupoids from this? So these groupoids will be free. So what we do is basically we consider the equivalence relation of being in the same leaf. So either I'm going to be, so for example, being in the same unstable leaf or being in the same stable leaf. So one way to say this is that X and Y are, say, unstable equivalent. And of course, I can do dually for stable equivalent. If when I take the iterated image of F inverse for X and Y and I measure the distance, it will go to 0 when n goes to infinity. So basically, the past of X and Y will get closer and closer. So this tells me that X and Y lie on the same leaf for the unstable splitting, the unstable coordinates.
I have a question.
Yes, please.
About this Haar system. So Haar system neither is unique, sometimes it doesn't exist. So what is the source of this Haar system here in this example, in this class?
Okay, so I'm going to give you a cheating answer. Well, see, if you take this groupoid, so there is a standard technique to take a groupoid and reduce it to an état groupoid by via Moride equivalence. So usually what you do, for example, in foliation theory, you will restrict to a transversal of the foliation.
Okay.
In this example, we actually have a canonical choice of transversal because we have 2 foliations, and by definition, they are transversal to each other. So, for example,
yes.
Right. So for this unstable groupoid here, Ru of X, F, I can reduce it or restrict it to a stable leaf. And then after this, I have to retopologize the groupoid, and I will get a Moride equivalent groupoid which is étale.
Oh, yes.
So for an étale groupoid, you have your hard system, and then if this also tells you that it can be translated to the locally compact case.
So this comes from the counting measure in this stable direction.
That's right. Yes. Once you restrict to this stable direction, yeah.
Okay.
So well, this question is good because you just basically have me say this technical point here in green. So the thing about this is that I don't want to keep distinguishing between this RU of X and its Morita equivalent groupoid, which is étale. So from now on, I will use the same notation. And of course, in your mind, you have to remember that this is étale. And of course, when I consider the étale groupoid, its unit space is not going to be X anymore because I reduce it to a transversal. It's going to be some piece of a stable leaf. But that also I will basically forget.
It's X all the time, the compact manifold here.
So this X is my compact space, and RUX has as unit space X. But then to get an étale groupoid, I will have to reduce RUX to a transversal.
Yeah.
And once I do that, the unit space is not going to be X anymore. It's going to be basically a piece of a stable leaf.
Yeah. Yeah.
However, I will not denote this differently in the notation. I will always write RUX because it's going to make things much easier. It's just there's going to be two notation otherwise.
Sure.
So the sister algebra is then the reduced groupoid sister algebra of this equivalence relation.
Mm-hmm.
Okay, so one interesting and more maybe dynamically motivated approach to studying this is to use a theorem by Bowen, which was improved by Putnam. So I talked about ample groupoids, and so because I want to consider not just étale but ample groupoids, I will say something about the more general case, but so let me just assume that when I have this main space X, when I reduce to my transversal, the stable foliation is going to be Cantor-like. We saw that this actually happens quite many times. So in that way, the RUX, that groupoid will be ample. So if it's not ample, then this Bowen-Putnam theorem still holds, but it's more complicated. So in this situation where I have a small space whose stable leaf is totally disconnected, there exists one shift-to-find type. In general, there would be sort of like two spaces mapping down, but let's look at this example, well, this case. So I can essentially find what's called the symbolic coding. So I can find a shift-to-find type which maps onto X surjectively and then equivariantly, so it will respect the dynamics. And most importantly, it's going to be étale on the stable coordinates. So this is called an S bijection. So this is a bit technical, but you should think of this as a way to take a small space and understand it through a simpler space, which is a shift-to-find type. So that's why we call it symbolic coding. So a very simple example of this. So consider this X to be this dyadic solenoid. So this was this Smale-Williams map of the torus that gets you into itself. If that's your X, now by the theorem, there should exist some sigma which maps onto it. And the sigma is just the full two shift. So it's the shift on two symbols. And so how do you get this map? So it's actually quite easy. So what you do, you just take the binary expansion of a number on the unit interval. Then you exponentiate the interval to code a circle. And then remember that X is a projective limit of circles. And this will give you basically this summation here. But basically this phi comes essentially from the binary expansion of a number.
I have a question. Is it as bijection preserved this hard system?
So this bijection will so this bijection, once you consider it, what it does on the groupoids, it will actually put one groupoid inside the other. as an open subgroupoid. So in particular, then you can use the Haar system from the bigger groupoid, which is just the countable one.
Does it imply that sister algebra associated with this measured groupoid is invariant under these S bijections?
So well, yeah, once again, so if you want to look at what is yes.
Okay.
Yes. So this is actually, that's why I don't want to, right? Because this is actually kind of technical. So if you want to understand what this S bijection does to the groupoids and to the sister algebras, is always, basically you always have to pass through a Moride equivalence, and then you can see. Because the Moride equivalence, see, this S bijection is a local homomorphism of the stable coordinates. Yeah. So we do the Moride equivalence exactly to reduce to a stable piece. To a stable piece of the leaf. So then we can see what's going on. So that's exactly what I was gonna say. So, okay, so I have this example here. But now in general, if I have my Smith space X and my S bijection coming from the Bowen-Putnam theorem, I want to see what this bijection tells me at the level of the associated groupoids. So the groupoid associated to sigma is Ru of sigma, and then the one for X is Ru of X. And remember, these are basically equivalence relations. So I don't really need to worry about the arrows, just they are determined by source and range. So it will give me an open inclusion. So because I want to talk about this example of hyperbolic dynamics, but I also at the same time want to talk about the general case where the groupoid is just given to me. I don't know it comes from hyperbolic dynamics. It's useful to just also generalize. Suppose I have some ample groupoid G and an open subgroupoid H. Then in the case of hyperbolic dynamics, I will assume that this is given by this Bowen-Putnam theorem, but in general, I can just assume this. And now for later, if we want to somehow compute K-theoretic invariants associated to this situation, then of course it seems natural to consider the equivariant Kasparov category associated to G and H and understand what this inclusion does at the level of this adjoint situation between, so the induction factor from H to G and the restriction factor. So this is something we are going to do later, but let me just say one thing. So in the general case where I have just some H and G and I don't know where they come from, there is always a canonical choice for H, which is just the unit space. The unit space is an open subgroupoid. It's quite simple, but it's very good. It's good that it's simple. In the case where I have groupoids coming from dynamical systems, like in this case with sigma and X, then H will not be the unit space. H will be this Ru sigma. So it will come from a symbolic coding. So I want to keep these two paths sort of open at the same time. So I have a canonical choice when I don't know what to do, basically. But then if I have more information that I know I'm working with these hyperbolic dynamical systems, then I can make another choice for H. I would call that a dynamical choice. And that's in contrast with this canonical choice.
I have a question.
Yes.
What kind of morphisms between groupoids lead to such a joint situation?
It's gonna be in a few slides. So I'll answer your question. So actually, exactly this. So, well, for K-theory, because it's, I guess, a bit familiar to people in this audience, that's what I wanted to say. But before getting here, I want to look at the case of homology. And there we will understand exactly what morphisms we need to look at. Okay. So let me go into this homology section. So first, just to make sure we know the basics. So if I have a groupoid, well, it's in particular a category, and so I can consider it NURB. So that would be sort of the standard bar resolution. It's going to be a simplicial, well, in general, it's a simplicial set for a category, but this is a topological groupoid, so it will be a simplicial space. And it's going to be what you expect. So at level 1, I have 2 maps given from range and source. And then in general, I will have a map which removes the first entry and another map which removes the last entry. And then the intermediate maps will just compose the elements in between. So I will have all these phase maps, and I don't need to care about the degeneracy maps for today. So this is for étale groupoids, and these structure maps are all étale maps. So
sorry, I have a question.
yes.
Could you come back to the previous slide? Yeah. In your construction of the nerve, if you consider only these phase maps,
Yeah.
So there's no topological problem with these projections because you are speaking about multiple fiber products.
Yeah.
Okay, so we are projecting.
That's right.
Do you assume that everything is Hausdorff? Or if maps are not proper?
No, so all I need at this map are local homeomorphisms, and for this I actually don't need to have Hausdorffness on the arrows. Actually, this is fine.
So still we are speaking about étale groupoids.
Yes.
Okay. Okay.
And when you speak about degeneracy maps and insertion of units, because it's a groupoid, not a group, do you choose your unit randomly? Oh no, it's probably I get it. It's the unit which is at the range of 1G and at the source of the following G.
Yeah, exactly. So there is a
Yeah, thanks.
yes. So as I said, I want to look at this adjoint situation not in K-theory, but in the case of sheaves equivariant over a groupoid. And of course, this will go back to your question that I need to understand which kind of morphism I consider. So let me first agree on what is a G-equivariant sheaf, and I will always talk about commutative groups. So one way to define it is just a G space F whose structure map, which goes from F into the unit space of G, is surjective and it's a local homomorphism, and the fibers are abelian groups. So this is what the French would call the étalé space associated to a sheaf. And of course, the sections of this F, these are exactly when I evaluate my sheaf on some U, that will get the sections. So, well, one thing you do usually with sheaves is that you resolve them, and particularly nice resolutions are the so-called C-soft ones. So a sheaf is C-soft if anytime I consider a compact subspace, the associated restriction map from the sections is onto. So that's one thing. And so from now on, I will assume that G0 has a finite cohomological dimension. So I want to exclude cases like infinite dimensional manifolds and things like this. This is important so that I can have finite length resolutions of sheaves. So this is a technical condition that I want to impose. So let me tell you what group homology is first, and then we can look at this adjoint situation. So as I said, if I have a sheaf, I can consider this a C-soft resolution. So what you do is you take the Flaby-Godemont resolution and then you truncate it. And this will work exactly because of the cohomological dimension assumption. Then what you get by inverting the degree is a bounded below chain complex. And now you want to define the homology of G with respect to F, and that's the hyperhomology of G with respect to this chain complex, so of sheaves. So what do I mean by that? So it will be, so you get a bicomplex, and then the total complex of that, when you take homology, that's what you call hyperhomology. So how is this bicomplex constructed? Well, on one direction, it is exactly given by this resolution of sheaves. In the other direction, that's the arrow direction, it is given exactly by the nerve of the groupoid. So you have two directions. One is the arrow direction, and in that case, you will get the nerve of the groupoid, which will construct that chain complex for you. But then you also have the space direction, where you have this resolution of sheaves. So in the end, you will end up with a simplicial structure that looks like this. You consider compactly supported sections from the nerve of the groupoid into your sheaf, and you end up with this integer structure, but now instead of F, replace S bullet, and so you see that you get a bicomplex.
I have a question.
Yeah.
In the context of groups, forgetting about spaces for a while, okay? You can define a site of G-equivariant sets, and cohomology theory is constructed automatically from some Grothendieck yoga. Okay.
Yeah.
Now we are mixing topology on units of this groupoid, probably with this construction. So my question is there a single site in the sense of cohomology theory, in the category theory, for which you can speak about sheaves or objects having resolution in the sense of this site?
So there is a site around.
Mm-hmm.
The site would be basically what's sometimes called the embedding category of the groupoid. So basically the objects of the site will be this, the basic opens for some topology of the unit space, and then these inclusions like for a topological space. But then you will also have arrows coming from the bisections. So
Okay.
it's a little bit more than the site of a topological space. However, I mean, this will not give you one, in a way, this is just an equivalent formulation. It won't avoid the fact that we still need to resolve the sheaf. The only case in which you do not need to resolve the sheaf is when the unit space is actually totally disconnected, which is exactly the case I want to consider. For ample groupoids, then a sheaf over, say, a counter set is automatically C-soft. And then you don't need to resolve because the sheaf is its own resolution. But in general, say if you have a Lie groupoid over some manifold, then of course, being a G-equivariant sheaf is in particular being a sheaf. So you first need to resolve it. And then you want to resolve also the groupoid part of the equation, so the arrows. And that will give you a double complex. I hope that's kind of clear.
Mm-hmm.
Now, okay, here we come actually to your question. So I defined equivariant sheaves, and then I defined the nerve of a groupoid. So I defined homology with respect to some coefficient sheaf. And now I want to look at some étale morphism of groupoids. Now, in the abstract, I had something about constructing invariants using a bit of homotopy theory and borrowing a little bit from algebraic geometry. So what I mean by this is just very simple. I am very far from being somebody who knows algebraic geometry, but in that context, for morphisms of schemes and étale cohomology, Grothendieck introduced this formalism of 6 operations that you can consider on sheaves. And so a couple of these operations are actually interesting for us too. So there is this pullback, and then there's this push forward with compact support, which sometimes I will call, phi shriek. So because I actually give you the definition of a sheaf in the analyst way, the pullback is actually the easy one, because the way I define the sheaf, it's basically a bundle. So then the pullback is just the pullback bundle. So of course, if you give the definition of a sheaf as some pre-sheaf with some gluing, then this is more difficult to define, but it's just a matter of perspective. Then there is this phi shriek. This is more complicated. So for spaces, it is not so bad, but for groupoids, it actually is a little bit involved. And so I am actually in a situation where it will be a little bit easier. Let me explain without giving you all the details. So first of all, if this phi happens to be a Morida equivalence, then there is an adjoint equivalence between these two. But in general, so in particular, this phi shriek will be exact. In general, there is a left to right functor for this phi shriek. But then in the case where we have open inclusions, things are quite easy. And so this is actually the answering the question that you have. So see here where I consider this projection from G cross Y into G. So for this kind of morphisms, we have exactness of phi shriek and an adjoint situation of this type. So these morphisms are quite special. They are projections where basically you remove the space. So Y disappears. G cross Y goes into G. But my open inclusion of groupoids is basically of this type up to Moride equivalence, because H can be replaced by G acting on G mod H, and then I can get rid of G mod H. So up to Moride equivalence, my morphism is of this type. So there is a technical detail here, which I am not going to say much about, and that's that if I have a subgroupoid of a groupoid, it doesn't necessarily act properly, like it happens for groups. For groupoids, that's not necessarily true, but it acts in a way that's called basic. So in other words, this G mod H can fail to be Hausdorff. However, by using the notion of basic actions, basically, this sort of framework of Moride equivalence still works. And so this is still a reasonable way to do things. Basically, an open inclusion can be reduced to a type of map, which looks like this projection. And for this type of projections, I have an adjoint situations of this kind, and I have exactness of phi shrieks. So my left and right functors, I don't need to consider them.
I have a question. Is it the same as to say that you are doing homological algebra in the topos of J equivariant sets for point G, and then you are speaking about geometric morphism between two topoi, and this is your geometric morphism. It is this kind of morphism.
Right. So there is okay. Yes. So this phi upper star, it has, so there's this left adjoint, but it also has a right adjoint, which is phi lower star, and this is a geometric morphism of topoi, and when it is a Moride equivalence, it will actually give an equivalence of this topoi, sheaves of G over sheaves of H. So one of them is part of a geometric morphism. Yes.
Okay, good.
Okay, so whenever you have an adjoint situation, you get, by composing the two functors, you get an endofunctor with a unit, a multiplication, a co-unit. So you get what's called a comonad. And so you can use this to produce resolutions. So if you give me some sheaf, I can start applying phi shriek, phi star several times to my sheaf, and that's a resolution. Now, of course, resolutions are only good if you can compute stuff with them. So you want an acyclic resolution usually. And I don't have time to explain to you exactly why I'm in a cyclic case, but let me give you a few ingredients. So first of all, to check that this is an exact chain complex, it is enough to pull it back once again by phi star, because I only need to check at the stalks. And then I can use just the unit of the adjunction, and that will give me a contracting homotopy. So this actually explains that I have a resolution. Now for the acyclicity, Kranitz and Murdyke proved a Shapiro type lemma, which is also proved by Alistair Miller in the case, which is more special to ample groupoids, where we replace sheaves by modules, but that's an equivalent approach. So as I said, this phi shriek in general is not exact. So this Shapiro type lemma on the left, you see that I have to take hyperhomology, because in general this L will be a chain complex of sheaves. But for my case, actually, I can take homology in both cases. Anyway, the important part is that I can get rid of phi shriek at the cost of computing homology at H instead of at G. So this is the Shapiro type lemma. Every time I have the homology of G with respect to some phi shriek F, I can instead compute it for the H groupoid and get rid of the phi shriek. That's one. So that's of course useful because my resolution has a lot of phi shriek, as you can tell. The second part is how to deal with the fact that this monad here, phi shriek, phi star, is applied several times. So I want to make a trade-off. I want to make the sheaf simpler at the cost of making the groupoid more difficult. So here is how this works. There is a change of base formula. And now if you consider basically this diagram, where here on the top left, I have a pullback in the category of groupoids. So what I mean by this is that, for example, the unit space is not just pairs of units which map onto the same unit. It will be pairs of units which downstairs are connected by an arrow. And then the arrows would be the obvious commuting squares. Okay, so but what this change of base formula is telling me is that whenever I have this sort of Schrick star several times, I can sort of make the sheaf simpler at the cost of taking a pullback of groupoids. So for example, if my sheaf F was just the constant sheaf of integers, and I take K to be H, so this is a pullback over 2, H and K are the same here. Then instead of having this complicated sheaf, I can sort of complicate the groupoid and take this pullback. And then I'm left with computing just the homology with respect to a constant sheaf, but the groupoid has gotten the more difficult. So that's kind of the trade-off. Now, as I explained to you, I have two choices for H. One is the canonical choice when I have the unit space, and one is the dynamical choice. So for acyclicity, of course, I need to show that the higher homology vanishes, and then I need to compute the degree 0 homology so that I can understand my chain complex. So let's do this. So for the canonical choice, it is actually quite easy. So if my groupoid is just a unit space, so it's just a space, then you can see that this pullback of H over itself several times will become just the composable arrows n times. And then this is the homology of a space. And so the homology of a groupoid, which is a space, just reduces to the homology with compact support. Just the grading is different. So there is a minus in the grading. But except for this grading, I basically have homology. So if then we assume that we were working with ample groupoids, then this G0 is a totally disconnected space. And that means that the homology will be vanishing in higher degrees. And in degree 0, it will be just the compactly supported functions from Gn to the integers. So then my chain complex will look exactly like the standard chain complex. I mean, so this should not surprise you at all. Then you get essentially by the nerve of the groupoid. So you just consider all these integrally valued functions from the nerve, and with these natural differentials coming from the phase maps. Of course, what's more interesting is when I make my dynamical choice. So when I make my dynamical choice, so this homology of this pullback groupoid is going to be the homology of the unstable equivalence relation of my shift of finite type, but fiber product over itself several times. So they take the fiber product over the Bowen-Putnam map several times. So this is not really obvious because you are shifting from a pullback of groupoids to a pullback of Snail spaces. So there is actually a Morita equivalence involved here.
I have a question.
Yes, please.
It's a very interesting isomorphism in the second line, because one side is homology, the second side is cohomology. So it's kind of duality.
Sure, but the groupoid, this groupoid H is just a space, really.
Yeah,
so
I understand this. Yeah. So do you have in the general case a similar result, because you are considering two extreme choices?
Yeah.
This canonical choice for the space and the canonical choice for this RU. Okay.
Yes.
Is there a single isomorphism with left and right hand side comprehensible in some terms?
So I will show you in a few slides a duality which looks like the kind of thing it seems like you want to have.
Perfect.
With some conditions.
Okay.
So let me just go back here. So okay, basically we reduce the problem to computing the homology of the unstable groupoid of a shift of finite type which has been sort of fiber product over itself several times over this Bowen-Putnam map. So in some sense, I need to understand this unstable groupoid, but fortunately we already done this, maybe with different language, but other people did it for us. So this picture is just the same picture. I'm just telling you that, so this power partner map phi is generating a simplicial structure. And this simplicial structure is playing a role in computing the groupoid homology. That's all I want to say. Now, the groupoid homology is the group, the homology of this groupoid RU sigma for some shift-affine type. But no matter the shift-affine type, this groupoid is always AF. In fact, the sister algebra associated to RU sigma is exactly the AF core of the Kunz-Krieger algebra. And the fact that RU sigma is AF, tells you that you get an AF core in there. So it's the gauge invariant subalgebra. So what does AF do for us? Well, because homology basically is compatible with the inductive limits, then AF tells us almost immediately the higher homology is 0, because basically we can reduce it to the homology of full equivalence relations on a finite set. And then the H0 of this homology is an interesting group, which was studied by Krieger, is the dimension group. So let me just tell you a little bit about this dimension group, and then we will see some examples. So as I said, any shift of finite type is actually coming from the shift over a graph, like I said at the beginning of this talk. So the dimension group can be defined in this way, that this is not the original definition. So you take the free abelian group on the number of vertices, and then you consider the adjacency matrix, and then you let it act. And then you consider the stationary inductive limit. That's a dimension group. Now, this construction is functorial. So what it means is that if I look at this this top part here, this simplicial structure associated to sigma and phi, I can apply the dimension group to this structure, and then I get a simplicial group, so a chain complex. That's exactly what Putnam did. He defined the homology of X by finding a resolution with sigma, and then applying this dimension group, and then that will give you a chain complex. And now what we have proved is that the homology that Putnam defined by using the dimension group of Krieger coincides with the groupoid homology of the unstable groupoid. So on the left, we have an abstract group which can be defined for any étale groupoid, and it doesn't use anything about what the groupoid is. It just uses, canonical structure like the nerve, the bar resolution. On the right side, we have a group which has been defined using all of the information that we have about the dynamics.
Sorry, may I interrupt you for a second? Because it's very interesting for me. So I have a directed graph. I have, say, finitely many vertices, I assume.
Yes.
And you, out of it, you create what? G is a free group on these vertices. Am I right?
No. So G is just the graph whose vertex set is V.
Okay. And when you take this limit, what is K? The number of vertices?
No, that's exactly the point. So K is nothing. This is a stationary inductive limit. So K is actually just confusing you, I'm afraid.
Yeah.
So you just take A and Z to the V, and you take this limit to infinite. So the system is not indexed by K. So I should have probably not read. I just want to say that this is it's an inductive limit, and it's a countable inductive limit. I guess all I wanted to say is that this is a countable inductive limit.
And so, how?
So for example, you have the integers and the multiplication by 2, right? And then you take this. Yes. You take this, and you end up with the Z extended by 1/2. So it's that kind of stationary inductive limit. So, but the point of this construction is that it is actually functorial with respect to S bijection and with respect to all these phase maps. So if you apply it to the implicit structure here above, it will actually give you a chain complex. And so Putnam has used this chain complex to define the homology of X. Now, of course, you need to prove that this is not dependent on sigma and phi, which he did. But
So
so
the adjacency matrix which act on the Z to V. Okay, okay, I've got it.
that's right. Yeah,
Thank
yeah, yeah, yeah. So it's a, I think it's a very standard construction.
Sure. Just notation is not obvious.
Exactly. Yes. Yes. Indeed. So this is a different type of language, and the K is maybe a bit confusing. I'm sorry about that.
Okay, could be omitted.
Yeah.
Yeah. Anyway, so we have this result. Let me state it a little more clearly. So the homology of main spaces is isomorphic, which was defined by Putnam, and uses just dynamics.
I have a question. What is
Please,
this underlined? Z underlined, what do you mean by
Oh, I just mean the sheaf.
constant sheaf?
Yes.
Okay,
Yes. Yes. It's just to distinguish the group from the sheaf.
okay.
So by virtue of this theorem, so because the homogeneous main spaces has a construction which is quite ad hoc, but the homology of groupoids instead admits quite a bit of machinery. So now we have this machinery that we can apply to the case of hyperbolic dynamics that we couldn't apply before because we didn't know the groups were the same. And so I just want to give you some standard examples. So for example, these homogeneous main spaces didn't have a Kunet formula, or rather, nobody could find it because the definition was quite involved. But once you reduce the definition to just the homology of a groupoid, then there's standard machinery for that, and you get a Kunet formula. So that's one example. This corollary, so there is a lot to say here, but just to be brief, this is the kind of thing you asked about, I think. So if we have a main space with the condition that the unstable foliation is like Rn for a fixed n. In this case, we have Poincare duality. So the homology of this main space shifted by n. So the homology at degree k is the cohomology of the space, not as a dynamical space, but just as a topological space, shifted by n. And so this works when you have an orientable space, but when it's not, you can, of course, twist by the orientation sheaf, and you will still get the result. So this is analogous to Poincare duality for manifolds. So this is basically a Poincare duality type theorem for hyperbolic dynamical systems. And so the way to prove this is to basically replace what you have on the left, this main space homology, by groupoid homology, and then making use of the assumption on the unstable set in some clever way, which I can't go into now. But, I just want to tell you...
Sorry. Could you explain to me these coefficients on the right-hand side? Usually, if you speak about Poincare duality, you are taking the tensor product with the orientation sheaf. Here it's a fiber product of Z over Z2 with this orientation sheaf. So it doesn't look like a twist by an orientation.
Yeah, I mean, so the stock of O is it has just two elements. And then to get the orientation sheaf, then I have to make this construction. So I am using the Cartesian product here because I'm always viewing sheaves as this type of étalé spaces, like bundles. So in the end, this is exactly what you expect.
Yeah. So first of all, I cannot see the map from Z to Z. From Z to Z2, it's obvious. But from the orientation sheaf to Z2, what is this?
No. So the stock of O has only two elements, and so the cyclic group of order 2 acts on it.
So I understand now. So you are talking about the action of the involution on the orientable, in fact, this unstable orientable covering.
Yes,
so
exactly.
Of the involution. Okay.
Yes.
Now I
So
get it.
I can either stabilize or flip the orientation.
Yes, thank you. Yeah.
So using these results, let me just give you some computations. So we had this example coming from number theory, where they have p-adic numbers, q-adic numbers. So the top part of the slides is the same one I showed you some time ago. So in this case, the local structure for the unstable set looks like R times Cantor. Now, I want to give you this example in particular because in my statement of Poincare duality, I have the condition that the unstable foliation looks like Rn. So in this case, I have R times Cantor. So this Cantor part seems like I can't apply it because, you know, I just said Rn. But then the same type of proof actually gives us something which I wouldn't call a Poincare duality, I would call more like a Thom isomorphism, and it still works. So this counterpart doesn't really bother us. And so, okay, so there is some computation involved that I'm not showing you, but the result is that there is a shift happening where I can get rid of this infinite place completion, this R, this is the, you know, given by the infinite place on there, and I can get rid of this R and just stay with the p-adic numbers. And then, because of this shift, I will have homology in degree negative, 0, and nothing else. And it is what you expect. It is just z extended by 1 over p and z extended by 1 over q. The second computation is about the Anosov diffeomorphism for the hyperbolic map. So it's actually interesting that I can interpret this in a number theoretic way. So in a way, this is actually a special case of the previous case, but it doesn't look like so. So what I want to do here is, so you choose this number, 1/2, 1 plus square root of 5. This has to do with the eigenvalues of A, of course. But now instead of considering the rational numbers, consider the extension. So this is a degree 2 extension, so it's a number field. And then the ring of integers will be just Z2. And then I can consider my completions. But now in this case, the relevant places to complete will be just the usual absolute value, and then the absolute value which I obtained by twisting by sending C to its Galois conjugate. So, but these are both Archimedean places. So in the end, what I get is just Z2, and then this will give me the torus by passing to the Pontryagin dual. So in other words, A is actually the matrix presentation for the multiplication by C on the ring of integers for this number field. So under this interpretation, I can actually apply basically the same result as before. And then I can say that for the unstable equivalence relation of this hyperbolic map, the Groupoid homology at degree k minus 1 is the same as the cohomology at degree k of the torus. And so now I will have non-trivial homology in degree -1, degree 0, and degree 1. So this is another example computation which I can do thanks to the duality, which is this last theorem here at the bottom. So I can see that I'm approaching my time limit, but I got several questions. So I hope that I can at least go through a couple slides here, but I will be quick.
Okay.
So I just talked about homology. I want to say a couple words about K-theory. So in the abstract, I had something about algebraic geometry, something about homotopy theory. So this theorem is by Dell'Ambrogio, Emerson, Candelacchi, and Meyer. It basically tells us that we can get a functor from KK into the stable homotopy category. And so I'm not going to use this really, but this should at least convince us that there is some homotopy theory to do in KK theory. And in fact, KK is a triangulated category. And actually, more recently, it is all known that this is actually a stable infinity category. So, for example, mapping out of C will give us, will give us spectra right away, and this will be a refinement of the theorem above. So, because stable infinity categories are not so familiar, I think with some audiences, I will stick to the triangulated structure because that's easier. But in principle, this can be done in a different way now. So I had this adjoint situation as before. So this was where we started. This was our motivation to go through sheaves. So once you have an adjoint situation of this type, you can basically define contractible objects and projective objects. So something is contractible if, when I restrict it from G to H, it becomes, weakly contractible, it becomes 0. And something is projective if it is basically a retract of some induced object, or a direct sum of induced objects. So this gives me sort of notions of projectivity and contractibility. And because KK is a triangulated category, I can perform localization. So I can localize at the contractible objects. So what this tells me is that there is some functor which can be characterized as the left adjoint to this localization functor, which I call P. Now, when I apply P and to some C-star algebra A, I will get, so it will come with the eco-unit. So I will get a map from PA to A, which I call D. So this is the Dirac morphism, which people in the Bancon conjecture should be familiar with. Now, NA is kind of measuring how far is D from being an isomorphism. So in a way, I want to compute N of A. And so this works in this way. So we have to construct a projective resolution for A. And of course, we do it exactly in the same way as we did it for sheaves. We compose induction and restriction, we get a comonad, and then we repeat it many times, and we apply it to A. And this will give us a projective resolution of A. And now I can construct this diagram, which is constructed by Rathmeyer. Basically, I have this map from P0 to A, and I can embed it into an exact triangle. And then I can lift the map using the projectivity of P1, and then I can embed into a triangle again, and I can go up like this. And so you see that now on the top line, I constructed a linear inductive limit of n i's. And the claim is that my N of A, which is measuring how far is D from being an isomorphism, is exactly the homotopical limit of these n i's. So in general, homotopical limits do not behave very well in triangulated categories, but for diagrams which are countable linear diagrams of this form, it's okay. So I have an exact triangle of this type, and from this structure, I can construct an exact couple and a spectral sequence. And I will end here. So, right, so there is some, of course, some work to do to identify really this D with the assembly map, but it is possible. So D is basically the Dirac morphism for the assembly map. And the exact couple that is built out of this tower gives me a spectral sequence. Now, the spectral sequence has in the second sheet, the K3 groups coming from my projective resolution. The dot was coming from this induction restriction applied several times. Now, of course, I did all of this work to define groupoid homology, so it would be nice if I can identify this second sheet with groupoid homology, right? Because this K-theory of P cross G is quite abstract, and that's the claim on which I want to end. So every time we have a G-sister algebra for G ample, the K group of A is actually a G sheaf. And so then we can combine everything we did in one diagram. We can construct G sheaves and H sheaves out of C-star algebras. And then we have a compatibility of adjoint situations. And so by way of this diagram, you can essentially identify that the second sheet here will have the homology of G with coefficient in the G sheaf associated to your C-star algebra. So the final theorem is if I have an ample Torsion-Free isotropy groupoid G acting on a C-star algebra A, which also satisfies the Bancon conjecture, then the K-theory group of the groupoid C-star algebra is approximated by way of a spectral sequence by the homology of the groupoid. And this has a version also with coefficients, which you see above, where I have the cross product of G and A, and the homology of G, and that's why we need to consider sheaves, not just the constant sheaf of integers. Now I have to put the coefficient, which is going to be the K-theory of A. So that's the theorem on which I want to end. I have some corollaries, but you know, it's late, I'm over time, so I'll just end here and let you read these corollaries if you want. Thank you for your attention.
Thank you so much. All right, are there any further questions? Ralph, would you like to weigh in?
Well, I remember that in Ian Putnam's theory, there was a version with two variables, or maybe was it negative indices or something? Do you cover the whole generality of that theory, or is there a restriction like this existence of this sigma?
So you're right. So in the general case where we don't assume the stable foliation to be totally disconnected, this Bowen-Putnam map is not actually one map, it's two maps. And in that case, so the result about the homology, I still have it, and this is the sort of the more recent stuff. So the groupoid homology will still be the same as the homology of Putnam, even when we have this sort of bivariant way of resolving the Smale space.
Oh, very good. So you didn't talk about it, but you do have this more general result.
I do. It's just that it's extremely technical, and
I imagine, yes. So it's good not to talk about it, maybe.
The indices explode a bit, so I didn't want to say it. Yeah.
Okay, great. Anybody else from the Zoom? I don't see any raised hands. So how about the room, Tomek? Yes.
Yes, I have a question about these negative indices and so on. Could you come back to your resolution you got from this monad?
In KT or in KT or in homology?
In homology.
Okay.
Okay. So you are substituting this simplicial resolution of F to something of, oh no, everything's okay, because now we have homology. Okay, that's okay. Sorry.
No, it's okay.
So the last thing I remembered was that you were passing dually to the cohomology, and then I created in my imagination fake impression that
right, yes.
Yeah,
no,
yeah.
so the reduction to homology is really, you know, there's some shift going on, and also as you can tell, the K goes to a minus K, so that's, you know, that's the right thing to do.
So it's important that you are speaking about homology in this.
Indeed.
Yeah.
Because see, actually, well, maybe I should, yeah, so in this slide, you can see that the spectral sequence is actually not converging to, you know, so K theory should really be called K cohomology, right? But on the left-hand side of the Baum-Cohn conjecture, we actually have K homology.
Yeah,
and
yeah.
then it is correct that the spectral sequence is actually converging on that side, on K homology, as you can see from this diagram. It's only by way of the Baum-Cohn conjecture that then I can make it approximate K cohomology. But in principle, I'm really approximating homology with homology, so everything is compatible.
Yes. So it was very true what you said at the beginning, that you are looking for the generalization of the group, not of the space.
Yes.
Yeah.
Especially with these ample groupoids, they are very close to being a discrete group. You know, the space direction doesn't create many problems. Yeah.
Okay. I guess. Thank you.
Anybody else? No, we're happy. All right, so it seems like we have finished the 2023-2024 academic year. So let us thank Valerio again for a very exciting talk. Thank you so much.
Thank you.
And I officially announce the beginning of a summer recess and stop recording.